All right, so this is going to be the second talk of the day, the last talk of the day. And it's my pleasure to introduce Li-Cheng Tsai. He's going to tell us about the weak noise theory for the KPZ equation, large deviations, I assume. And Li-Cheng is now currently at University of Utah, and I'm happy that he's here and joining us and giving this talk. Thanks. Thanks, Axel, for putting together this meeting. Thanks, Axel, for having me here. And thank you all for coming. As the title says, I'm going to talk about weak noise theory for the equation. I want to start off the talk by telling you what the KPZ equation is. It is a stochastic partial differential equation introduced in 1986 by three physicists, Gaudreau, and John. So what they had in mind was a type of random growth model. So here you see an interface, and we're in one space dimension, so X, that one space dimension is growing time. Okay. And the thing that are featured in KPZ equations are three parts written here. The first thing is that there's a random forcing, ambient forcing, that is driving the whole thing to grow. And it's modeled by a space-time white noise. So I'm not going to define space-time white noise. You should think of it as, some rough noise that is uncorrelated in space and time. It's a discussion, but it's not relevant in this problem. Actually, a little bit. And that thing is driving the whole surface to ground. You can think of it as snow flowing from the sky, and that's the sort of the pile of the snow. Or if you are trying to grow a membranous, laboratory, you can think of it as gaseous particle being bombarded onto the substrate. Okay. Now, on top of that, there are two physical mechanisms of the interface to reconfigure itself according to this ambient forcing. One of them is a smoothing effect given by Laplacian. It says that locally, this surface has a tendency to smooth itself out, according to this Laplacian. On top of that, there's a slope-dependent growth. So this is a quadratic function of the slope. What it is saying is that locally, the height is going to grow at a speed which is a half of the square of the slope. Now we're wondering, why do I put square here? So physicists have this heuristic. If it was a quadratic function, if it were a generic function, I'm going to tailor expand. The first one is a constant. I can remove the constant by just an overall changing an overall growth speed. And if I have a linear thing in x in the gradient h, I can remove it by doing a Galilean transformation. Move along a constant velocity. So quadratic function is sort of the first non-trivial slope-dependent curve, and can say for closest. All right. And so what we're looking at is the what's called Freidlin Wentzell Large Deviation Principle for the KPZ equation. What does that mean? Okay, so let me try to break it down. So the first thing is I'm going to put a small parameter in front of the space-time white noise, square root of f1, and I'm going to let f1 go into 0. So that's just the setup. Okay. And so Freidlin Wentzell large deviation remains in this building. I'm going to look at the large deviation principle of the corresponding solution, where large deviation principle will be one way. Okay. Now this, introducing a small parameter thing is pretty common in stochastic analysis literature, and that's really where Freidlin Wentzell came from. That's just a standard setup in that literature. And if you don't like that, there's a different way to look at it, which is you perform a change of variable here. Okay, and what that does, it kills this small parameter, but it brings the space-time unit to a short time unit. So you're looking at the unscaled KPZ equation over a small time window. Okay, so throughout this talk, my time horizon is going to be from 0 to 2, and space is the full real line. Okay. This 2 is just purely cosmetic. It makes various constants for you. You can do pi. Okay. Any questions so far? All right, so that was the setup. So what is a large deviation principle? So, roughly speaking, it studies atypical behavior of the process. Here is the height function as f1 goes to 0. Okay? So before talking about atypical behaviors, let me first discuss what are the typical behaviors. If I set f1 to 0, what's going to happen? Well, intuitively, you see a small parameter here. So you will guess that you simply just wipe out this guy. And that's indeed what happens. If I just look at this solution to this PDE as f1 goes to 0, the typical behavior of H, the random profile, is going to converge, approximate the deterministic profile, which solves this deterministic, which simply just wipe out this guy. Okay, so here's a schematic showing of what that looks like. You know, this curve is the solution of this deterministic PDE, and your HF is going to hover around. That's the typical behavior. Okay. I'm not looking at typical behavior, I'm looking at atypical behavior. So put it differently, let's say I pick my favorite point, x equal to 0, and t here is equal to 0. Instead of looking at high function around this point, I say, what is the probability that's going to be here? Or what is the probability that's going to be here? The probability is going to be small because, you know, we know it's going to concentrate around this point. And, you know, that's sort of this schematic showing of what happened. So if you plot the distribution of the high function at that point, it concentrates around, you know, where the PD tells you it should be. And but there's a small probability that's going to be down here or up. And we want to study that probability. That's, you know, that's the sort of the setup for large deviation principle. Okay, so let me be a little more concrete. Okay, so I'm going to pick a point along this axis that is not the typical value. I want to ask, what is the probability that my high function at that point approximates that value? And it turns out the probability is going to be small, exponentially small in the parameter. The scale is going to be exponential minus 1 over epsilon. So that's a small probability. And on top of that, you'll see a coefficient in front of the exponentially small probability. And that's fair, right? Because, you know, if you're twice as far as, you know, if you move further away from the typical value, this probability would be smaller, and hence this coefficient should be bigger. And the same here. And the goal of large deviation principle is to point out that speed, which I already told you, 1 over epsilon, and also characterize this coefficient, which is called the rate function, as a function of how far you're deviating from the typical value. So it's a function of lambda. Okay. And in this example, I'm just probing the high function at 1 point, t equal to 2, x equal to 0. So that's the 1 point rate function. Okay. And the throughout this talk, I'm going to be a little bit informal, imprecise. You know, this means h around lambda, and this probability approximately that. And for once, I'm going to write down what exactly that means. So this is exactly what it means. You know, approximately lambda means, you know, I have a small delta, and this difference is less than delta. And this approximation means I take log and multiply this by epsilon, and the limit is equal. Okay, but for this talk, I'm going to mostly operate on this informal one. Does that make sense? Yeah.
So that means epsilon to 0 first, and then delta to 0.
Yes. All right. So that was an example of 1 point. But besides 1 point, you can look at this thing. You know, it's a space-time function. You can look at this thing as a process level. So I'm going to think of h as a function of these two variables, t and x. Okay? And I give you generic possible trajectory or shape of the height function. I can ask, what is the probability that the entire height function approximates that shape? And just as before, the speed is going to be epsilon inverse. And in front of it is going to be a coefficient that depends on the entire shape, which we are called g. And g is just a generic function. It's called a deviation of, you know, your h epsilon. And I here is the rate function, but now this rate function is at the process level. Okay. And as I said in the previous slides, these are a little bit informal. There's a precise way we can present here. I wrote this just because I want to prove you that I'm a mathematician, but I'm not going to worry about it. Okay, so it's really just a formal version of what's written here, but throughout this talk, I'm going to operate at this informal one.
Wait, sorry, so the too long didn't read. So the thing on the bottom is the part that's too long. Not read. The thing on the top is bigger.
Yes.
Okay, just making sure.
All right. So I hope the idea of process level large deviation makes sense. And on this slide, I want to sort of motivate you why would we care about such a question, right? Large deviation is a question about rare events. So typically the probability of them showing is very small. Typically they don't happen. Why do I care? I'm going to answer this question, I'm going to steal a word from stochastic chapter. So you can ask about the question of what is your probability of winning lottery? That's very small, right? It's not very interesting. But there's another question that might be more interesting is what's my life is going to be after I won the lottery? That's arguably more interesting question. As it turns out, in order to answer a second more interesting question, it's helpful to answer the first question at the sort of more elaborate level. So what's my life is going to be after I won the lottery? Am I going to still ride the subway to work, or am I going to ride a helicopter? How do I answer that question? Well, I can look at the probability that I both win lottery and ride subway to work. That's a small probability. And compare that with the probability that won lottery and ride helicopter to work. That's also a small probability. But even though both of them are small, I can ask which one's bigger. If among these two small probabilities, that my chance of winning lottery and riding a helicopter to work is bigger, then that's more likely, right? And that's the idea of large deviation. So let me try to generalize that, that example here. So here on the left, I'm showing you is the typical shape. This is not described by the partial differential equation. Just a note, the t-axis here, x-axis here. Now, let's say I perturb this height function. I perturb this function at one point, my favorite point, 2, 0. So t equal to 0, t equal to 2, x equal to 0. I make it bigger. Okay, imagine I take a pole and then just poke it. What is the shape going to be like if I do that? And mathematically, how do I formulate it? Well, the way I formulate that is, what is the shape of the random height function if I condition its value at this one point, right? This picky function? What is the most probable shape that's going to follow? Well, this event doesn't happen, with high probability. It happens with a small probability. But what you could do is examine all possible shapes that attend such a condition. And among all possible shapes, you pick the one that is most likely. Now, remember the probability is described by e to the minus speed times rate function, right? So among all possible shapes that achieve this conditioning, the one that minimizes the rate function, hence maximize the probability, is the most probable one. So this turns the question of finding the shape into a variational problem. The most probable shape, if it exists, is the minimizer of the rate function subject to the condition I imposed. Yes.
Did you specify an initial condition?
I have not.
This is just a picture.
It's just a picture, yes. So far, I have not specified. I can tell you when I drew this, these two initial conditions are the same. Okay. I make sure that happens. Any other questions? All right. So that's sort of the main motivation of of this talk. The reason that we study large deviation principle is to be able to tease out this most probable shape. Okay. So here's a sort of a summary slide of what's been done in studying the Freidlin Wentzell or short time large deviation principle for the KPZ equation. Okay. And so there are basically 2 + 1 approaches that are known. So on the left is the exact formula approach. Okay, so what happens is that the 1 point Laplace transform of the exponential of the KPZ equation admits some Freidlin determinant expression under some special initial conditions. And you can try to extract, 1 point large deviation rate function from that formula, has been done by these physicists. Okay, so it's not 100% rigorous, but the analyses are very convincing. Okay? So that's the exact formula approach. And on the right here is what physicists call the weak noise approach. So it is in line with what I just talked about. They look at the process level rate function, okay? And then they turn that into a variational problem. If I condition at 1 point, then the most probable shape is the minimizer of the rate function. And not just that, the 1 point rate function is also the minimum of that variational problem. And these folks, they're all physicists up here. They use that to extract a lot of information, and that goes under the name of weak noise theory. And these are mathematically rigorous results. Okay? So this talk is not focused on the right hand, the weak noise theory. And pretty recently, starting last year, it was realized that there's a way to combine sort of exact results with the weak noise theory result, which is from analysis. And I'm going to briefly talk about this at the end, if I have time. So basically what happens is that if you look at the variational problem here and you derive the Hamilton equations, it turns out that equation, after some transformation, is the cubic nonlinear Schrodinger equation, and then you have this whole machinery from integrable. Yeah, so that's recently realized. And yeah, I'm sorry. That was yeah. So that's something I'll talk about at the very end. Good. All right, so the first result I'm going to tell you is about the process level rate function. Right? So in order to initiate this entire study, the shape of most probable shape, there's a variational problem that we need to solve. But before even solving that thing, what is objective function that we're minimizing? So I'm going to tell you how do you describe the rate function for the large deviation principle of the stochastic capacity. So the result is as that this thing satisfies large deviation principle. We speak from inverse and a rate function I. So what is this rate function I? Well, in order to explain to you what this rate function I is, let me first take a look at the noise itself. Right? So this whole this KPZ equation, the only part that is explicitly random is this noise term. And let's try to just study the large deviation principle of that noise term. Okay. So slightly informally, I'm saying, what is the probability that the noise, straight-line Y noise, approximate a generic function rho? Okay, what is that probability? Well, the probability is epsilon, the speed is epsilon inverse, and the rate function is simply the altitude norm squared of my deviation rho. Okay, and that's a classical result. I think Yier explained this in his background talk, and also informally, but I think he explained that. So I'm going to just assume this and move forward. There's actually an easy way to see why the speed is epsilon minus 1. So remember that KPZ space-time Y noise is actually a Gaussian process. So what is multiplying this Gaussian process square root of epsilon is the standard deviation, right? Now remember in Gaussian distribution, let's just take one-dimensional Gaussian. It's exponential minus variable square over twice the variance, right? Twice the variance is what? Sorry, not the 1 over the variance is what? 1 over the square of that. And that's where you get this 1 over, and this half actually comes. It's 1 over 2. So that's how you understand the speed. And the rate function has involves a level 1 calculation, which I won't go into. Okay, so that's the deviation if I just look at the noise. Okay, what happens is that you take this as the input and you plug it, and this thing drives the entire process to burn, right? So what is a natural guess of the rate function? Well, if my space-time Y noise approximates rho, maybe I can just replace this whole thing by rho, plug it in, and then solve the corresponding PDE. And that's actually what happened. Okay, so the rate function is given by the following reference. I can see a generic rho, and this rho should be thought as a deviation of the space-time Y noise. I plug it in and solve the corresponding PDE. Now I record the solution as a functional of that rho. This rho is a generic functional that can describe how the noise, ripple in space and time. Okay, and for each such, ripple I have a corresponding height that depends on the ripple. What is the cost of, what is the probability of reaching such a deviation? Well, it's as that given by half of the square of the altitude. Okay? So if I want to realize such a generic deviation, what I do is I search for all possible ripple of space-time rho, such that the corresponding height function will match the deviation I want. And the cost of doing that is given by the rate function of the space-time white noise. And if there's more than one such rippling that achieves such a height function, I just take the most efficient one. This is have your slide to address any questions.
So your function G should be in the class of the kind of the functionality part, right?
Yes, so I'm taking the convention that if this thing is empty, then the empty is infinite. Okay. So if it's not even possible to achieve such a height, then the probability is just so small that I should define the rate function to be plus infinite.
And then you're going to move to an infimum of an infimum problem.
Yes, infimum is just one infimum, right?
Okay, I see. Great.
Or you can plug in the negative sign becomes the maximum of the variational approach, right?
Yeah, I would do info. Okay. Yes.
So when you solve for H, don't you need an initial condition?
Yeah, so the initial condition haven't set, but it has to be fixed. So everything has to be has to start from a fixed initial condition, including this big H. So
right. So that's related to the initial condition of the.
Yeah, so throughout this problem,
it's always the same.
It's always the same initial condition. All right. So actually, was one slide ahead of me. So, well, back to the question that we were interested. I got to probe the height at one point, my favorite point to 0, right? To be lambda. So what is that? Well, I'm going to look at all possible deviations that achieve this with the smallest rate function. But remember, the rate function is given by the recipe through this rho, which is the deviation of the noise. So I can replace this variational problem, which describes the most probable shape, in terms of a variational problem of rho, the deviation of the noise. So I look for all possible rhos, such that it satisfies a given initial condition, and it satisfies the conditioning value. If I plug it into this H, it satisfies this condition value at 2, 0. The cost or the rate function is the square of the minimize. Okay, so I'm going to jump between these two. Sometimes I'm going to phrase it in terms of rho, and sometimes I'm going to look at it at the level of height function, but they're the same. Well, as an analyst, the first two questions you ask is, does the infimum exist? Is it actually a minimum, or is it, is this infimum a tangent by some L2 function? And is the infimum, is the minimizer unique? Does there exist a rho L2 function rho minimum that achieves this minimum, this infimum? And if so, is it unique? Well, the first question is easier to answer. It has a minimum. This thing is attended by some L2 function. Okay, so the minimizer exists. The second question is about uniqueness. Anyone want to take a guess? No? No, because the way I phrase it. So there's no definitive mathematically rigorous result at this point, but several physics papers they show that for a special initial condition, the Brownian initial condition, there's actually a symmetry breaking phenomenon. So I won't go into detail of that, but what that implies is that if that symmetry breaking has to happen, that means the minimizer is not unique. There are two Actually, there are two minimizers that are in the mirror image of each other, and they're equally good, equally likely. So in general, uniqueness is not true, though in some other cases, in the case I'm going to discuss, it should be true. So it depends on the initial condition. Sometimes unique, sometimes not.
And it also depends on the value of lambda.
Right. So that's actually even more complicated. So for Brownian initial condition, it's not always symmetry breaking. So as you vary the value of lambda, for lambda very negative, there's no symmetry breaking. As you keep increasing it, at some point, the symmetry breaking happens, and then beyond that, always happens. All right. So finally, let me fix the initial condition that I'm going to work with. Because throughout this talk, I've been vague about initial condition. This slide doesn't work, I'm going to fix it. Okay. So I'm going to work with one special initial condition. It's called narrow wedge initial condition. In order to define it, I actually need to do some transformation. Okay, so let me bring our attention down to here. So this is the KPZ equation. It's nonlinear because you get this quadratic term. And it is a known fact going back to the 50s that for equations like this, you can apply what's called Hofkow transformation, which is simply exponentiating the solution to bring the nonlinear equation into a linear one. Okay, so down here, you see just a heat equation, the first two terms, and with the multicollinear noise. This is called stochastic heat equation. Okay. So that's a standard trick. You can linearize, you can get rid of this nonlinearity by doing this transformation. And now here you see a linear equation. And for linear equation, it's natural to consider fundamental solution, namely starting from delta initial condition. And that's what we're going to do. We're going to start this stochastic heat equation here from delta at 0. That's delta initial condition for stochastic heat equation. And these two things are related to each other by exponential or taking log. Okay, so I'm going to call the corresponding initial condition for that, for the KPZ equation, the narrow wedge initial condition. That's a pretty mouthful. So narrow wedge initial condition means I first exponentiate the KPZ equation, start the stochastic heat equation from delta, and then take log. Okay. Now, why don't I just spell out the initial condition for the KPZ equation? The reason is that it's actually not function, but it's not really, it behaves like this when t goes to 0. And when t goes to 0, the thing is like minus infinity. So really, the narrow wedge initial condition is something that is tending to minus infinity as t goes to 0. But, don't worry too much about it. The main thing is the first term. Okay, so as t goes to 0, what you're seeing here is a downward parabola, again, more narrow and narrow. If I'm going to plot this is a parabola that looks like this. It gets narrower and narrower, and that's why it's called narrow wedge. Looks like a wedge that is very thin. All right, that's the initial condition I'm going to work with for the rest of the talk. All right, so what are we interested in? Well, I'm going to start my KPZ equation from narrow wedge. I do my favorite condition. Yeah. Now, there's, did I say that? Oh, yes, I did. Okay. So the question about uniqueness. So if I do a conditioning like this, and if the level of conditioning is low enough, smaller than a fixed constant, this constant is explicit at the narrow line, then it is proven that the minimizer is unique. Okay, so we have a limit shape. There's under the narrow wedge initial condition, it is generally believed that there's a unique minimizer, and that is the limit shape. Okay. Well, okay, so it is there. So what do I want to know about it? Well, turns out that if you look at large value, or in this case, negatively large value of conditioning, lambda, you can say something pretty explicit about the limit shape. Okay. So I'm going to do this asymptotic result where not only do I do conditioning, and I push the level of conditioning down to minus infinity. And as that happens, it is natural to rescale your most probable shape accordingly. Like this. Well, this division by lambda is natural because the value of conditioning is lambda, right? So if I do that rescaling, the level of conditioning becomes -1. So this division by 1 over absolute of value of lambda just corresponds to that lambda. Bring the conditioning to minus unity. And this comes from the PDE square root of lambda. Okay, so here's the result. This is what I just finished with here. So as lambda goes to infinity, minus infinity, this most probable shape converges to something explicit. Okay, as I debated for quite a while to decide not to write down that something explicit because it's just a bunch of formulas. I'm not sure you're a big fan of that, but trust me, it is something explicit. And this something explicit has already been predicted by these physicists before. And here's a plot of that function, h minus. So again, t-axis is here, and this is x-axis. And this is the point on condition. Remember, it has been normalized, the value of condition has been normalized to -1. So that's -1. So that's the point on condition. And this light cone-like shape I'm drawing here is what the height function would look like if I didn't condition. So if I didn't do any conditioning, the height function would evolve like this cone-like shape in space-time. And if I take this point and condition it down here, it's going to look like this dark shape.
Quick question.
Yes.
Time is going forward this way.
Time 0 is here and 2 is here.
Okay.
All right. Yeah. So on this slide, I'm going to try to explain to you how did the physicists predict this limit shape. And the method is not totally sort of out of the realm of math. It's plausible that one can make reverse of their method, though that's not what I did this year. But still, let me explain what they did. Very briefly. Here's just some notation. So the unique minimizer, I'm going to denote the unique minimizer of rho as W. So W now is the minimizer of the deviation of the noise. And the corresponding most probable shape, I'm going to call it H. And you remember we have to perform scaling on both of them. So this is the scale version of the height function, and this is the scale version of the deviation of the noise. Okay. So
what does rho n means?
the minimizer, the variational problem, this variational problem. So what they did is, well, there's a variational problem. So you can try to perform calculus of variation. And what you get is the Euler-Lagrange equation. It's an equation that is second order in time. And you can turn that second order in time equation into a system of two first order in time equation called the Hamilton equation. So they did that. Okay. And the Hamilton equation is explicit. I don't have it here, but I have it last slide. And what they did is they performed scaling, the lambda scaling in that Hamilton equations, and they just formally take a limit at pretty formal level of that system of Hamilton equation. And they get a limiting equation when lambda is equal to infinity. They explicitly solve that limiting equation, and they found the solution, W star and H star. Okay. That's what they did. Okay. And that's probably the most explicit formula that I showed throughout this talk. So the W they found is this. It's not going to matter too much what it looks like, but I'm showing you anyway. And this L as a function of time that is obtained by solving implicit. Okay. So they found something explicit, and that's how they predict this one. Well, turns out that using some techniques, it is possible to show that the actual W lambda converges to the prediction W star in L2. And that's what I did with Yier last year. And this proof is still kind of mysterious to myself. It is the kind of proof that depends on knowing the answer. We had it been without them, we won't be able to prove. This proof actually involves knowing this thing and then showing that it's true. And yeah, so that's probably the most I'm gonna say about this proof. So what I'm gonna do next is to take this as given. Okay? Just given that we know the minimizer of the deviation of the noise converges to the prediction, how do we understand the limit of the corresponding most probable shape? How do we understand the limit of H? Okay? The thing I showed you on the previous one. How do we understand that if we assume we know that W converges to W star? Okay. And the tool that Yier and I use is the Feynman-Kac one. So what happens here is that, remember I told you about this linearization. You can go from this nonlinear equation to linear equation. And this stochastic, this heat equation with a potential can be solved by the Feynman-Kac formula. We can write the solution of the heat equation with a potential W in terms of a Brownian motion like this. Okay? So that's a formula. All right, so there's a lot of terms involved here, so I'm going to walk you through this formula piece by piece. So first of all, on the right-hand side, you see exponential of something. And that's something you see the function W. So the way I like to think about Feynman-Kac is that this W is a potential. Actually, minus W is a potential. It is the potential that is permeating space-time. It's given. Okay. On top of that, you take expectation of something which I call W. What is W? Well, W is a standard Brownian motion. Actually, not standard. It's a Brownian motion that got sent from the point Tx back in space-time. Okay, so I'm interested in the value of the function at point Tx. And what I do is I take that point. Remember, here time goes down. And so that time goes from 0 to 2. I take that point and send a Brownian motion going backward in space-time. Now here you see a delta function at 0. So this Brownian motion essentially has to go back to 0, 0 because of this delta function. And ask, where does this delta come from? It comes from the delta initial condition. Remember, in narrow batch, we take the initial condition for the stochastic heat equation to be delta. So that's where this comes from. Okay. So the way I like to think about it is you have a Brownian motion that is traveling in space-time and subject to the ambient potential given by this function W. Now, one more word about this Brownian motion. The Brownian motion has a small variance. It's 1 over square root of absolute value of lambda. So this thing really has a small variance. It has to come back to 0 because of the delta. All right. So as I said, I'm going to assume that this potential, what I know from the previous slide, the potential converges to a limiting potential. Okay. So what I know is that this potential that is permeating space-time is going to approximate a limiting potential, which is minus W star. Now, how does this thing behave accordingly? Well, you have a Brownian motion with a small variance. The variance is going to 0. It has to come back to 0. So without any ambient forcing, the most likely trajectory of the Brownian motion is just going straight, going from this point to this point, linear. That's the most likely trajectory of the Brownian motion, having without anything. But that is not the case. We have an ambient potential given by W star, right? So maybe the Brownian motion doesn't like to go straight. Maybe we want to go other directions so that we can avoid high value of the potential. So there's a competition between two effects. Brownian motion itself likes to go straight. It wants to minimize its thing which I call entropy. So this thing is measuring how straight the Brownian motion is going. But there's another thing that's coming into consideration, which is the potential energy that is playing at a vacuum. So as lambda goes to 0, what we expect for this whole thing to behave is that it's going to minimize, jointly minimize the entropy of the path itself, together with the potential energy that the path is feeling. Okay, does that make sense? And if you're familiar with Vardan's lemma, This is like in the context of variable. If there's a thing that's coming from the random variable, the rate function, which I call potential, and there's another, which I call entropy, and there's another piece in the expression that you're evaluating, which I call potential. All right, so this gives you a way of expressing the conjectural limit height, limit h, in terms of the potential. And remember this W star is explicit. So what you can do is you really just try to solve this variational problem explicitly, and that's what I did with you. So you can try to solve this variational problem, and for each point in Tx, going back here, you can try to find the path, the best path that connects you to the origin. And these paths are explicit. They're being shown. So if I'm here, I point Tx here, the path that brings me back to 0, 0 is this path. If I'm here, the path that brings me back to 0, 0 is this path. So every point comes back to 0, 0 because that's the delta initial condition. And everything else is being shown here. This L here is the explicit function I showed you a few slides before, it's explicit. And everything in between in this region is just a linear dilation of that function L. And what's outside of this region are straight lines, and they hit L or plus minus L at 10. Okay, so that's all the geodesics that realize this behavior. And once you have the geodesics, you can literally evaluate. Take a point here, you just evaluate this, functional along that geodesic. That is the value of h. Okay, and that's how I got this actually numerically. Does that make sense?
So once they hit the oval, they stay in the oval.
Yes. Yes. Going backward.
Yeah.
Let me just quickly say a few words about the proof. The proof really amounts to justifying the entropy energy competition. I said a few slides earlier. And on a technical note, the reason that this is not trivial is because in the Feynman-Kac formula, the actual formula here, this is not a W star. If I were to replace this W lambda with W star, this convergence would follow more or less standardly from Faraday's law. So what I really need to do is to be able to justify that passage of limit while the potential itself is changing, though it's converging to W star. Now, I'm already thinking, well, we do have a convergence. W lambda is converging to W star in L2, but it turns out it's not enough. There's a counterexample. If I only know the potential converges to a limiting one in L2, it is not guaranteed. There is a counterexample that the corresponding height function will not converge. So you need a little bit more, which is a bit technical. I'm not going to get into. Okay. All right. So that's the result. Okay, that's a result where you push the condition value down to minus infinity. Now guess it. There's a minus infinity result. There is a plus infinity result. So you do the same. You ask the same question. I start from the narrow wedge, and then I condition at one point. I send that point to plus infinity. What's going to happen? Well, you do a similar scaling. Okay. And what happens is that the most probable shape also converges to another explicit limit. And again, this limit has been predicted by the same group of people. And here's a plot that shows this. Again, this curve-like shape is what happens if I don't condition. What the height function is going to look like if I do a condition. And this is the point of condition. So the value has been normalized to. So imagine that, I take a pole and poke it. That's what's going to look like. All right, so before I move on, I want to tell you that what happens in the lower tail conditioning and the upper tail conditioning, the mechanism that leads to these most probable shapes are actually very different. So in the lower tail condition, where I've sent the value to minus infinity, what happens is that, well, I told you earlier that the deviation of the noise is going to converge to an explicit function, and that function is continuous. So what happened is that the contribution of the noise, the deviation of the noise to be precise, spans over a sizable region in space. On the other hand, if you do an upper tail condition and you send the value condition to infinity, the mass of the deviation of noise is going to always concentrate around x equals 0. So you don't see contribution of the noise outside of a small neighborhood of x equal to 0. So that's very different.
So could you explain why?
Yes, I'm about to. Oh, well, to explain why, let me take the Feynman-Kac formula and plug it into 2, 0. That's a point of condition. Remember? So what did we condition? Condition on that value to be e to the lambda. So it's either e to the large number, that's the upper tail conditioning, or e to a small number, minus number. So negative large number, that's very small, that's lower tail condition, either one. Let's take a look at upper tail conditioning. Okay. Well, actually, before that, let me remind you what are we doing here. So this is the Feynman-Kac formula, and I want this whole expression to be e to the lambda. And I'm going to look for. Not the way it's supposed to. Anyway, I'm going to look for the W that achieve this conditioning with the least L2 norm. And this is coming from the variational problem. Remember, the rate function, the cost of achieving height is the L2 norm of W. So I'm not only just making that equal to e to the lambda, I'm making that equal to e to the lambda with the most efficient W, the one that has the minimal L2. Okay, let's take lambda to go to plus infinity and see how can we do. So, well, I'm going to propose to make W, sorry, there are two W's, the potential, little W, to be large only around small corridor around x equal to 0, and it's 0 otherwise. Okay, that's my proposal. Does this work? Well, it kind of works, because what you're doing here is you are taking average over the expectation over all possible Brownian paths. And among all possible Brownian paths, there's some paths that's going to hover around the origin. Those paths are going to feel the effect of the potential if you make the potential big. And those paths will already contribute a large quantity. So this is a viable path to achieve e to the lambda, with small amount of L2 norm, because my potential concentrate around small region in space-time. So that's pretty efficient. So you might be wondering, well, if that works, why couldn't it work in the lower tail condition? Why can I not just make the potential negative around a small corridor around the origin? That would already change this path already. Well, but take a look. You are averaging over exponential of those quantities. You're averaging over a bunch of non-negative quantities. In order for a bunch of non-negative quantity to be large, just one of them needs to be large. But in order for them to be small, all of them or most of them have to be small. So only making those paths feel your potential is not enough in the negative case. You need most of the paths to feel a negative potential in order for this entire average to be small, and that causes a difference. Okay. Does that make sense? Good. All right, so here's a picture of the geodesics. So as I said, the noise is in effect only around a small corridor around the origin. So if I want to be a point here, okay, I go back to a type. The corridor around the origin is like a preferred region. So what's going to happen is I'm going to go straight to that place and then just stay. Okay. So here's then I'm going to go to that region and just stay. Except that if I'm too far out, it doesn't. The compensation doesn't work. If I go to that place, that will cost me too much energy, so I would just rather go directly to origin, and the boundary is here. So that's a picture. There's a few words about a proof. The first step in the proof is to try to argue that this potential should be approximately time dependent. And once that is established, you can try to turn the variational problem, which is a variational problem in space-time, into just a spatial variational problem. And that spatial variational problem can be solved by the GNS inequality. That's this stuff. Right. So finally, I realized since this is the integrable probability conference and there's nothing integrable so far in this talk, I should probably say something about integrable probability. Actually, not integrable probability, integrable system. Okay. So I told you that there are 2+1 methods, approaches to this problem. And the +1 is something that got realized last year. So you take the variational problem of this most probable shape, that's a variational problem, and you can derive the Lagrangian equation, that's the second order equation. You can turn that second order equation into a system of two first order equations, that's the Hamilton equation. So that's the Hamilton equation for the minimizer. Okay. And these folks realize that if you do this transformation, that brings the system into this system. And if you're familiar with the cubic nonlinear Schrodinger equation, this is just the imaginary type version. If I put an I here, I there, that's exactly the imaginary type nonlinear Schrodinger equation, or the sort of the pair version. And it's integral. So Alexander Kornberg and Pierre, they wrote a series of paper, deriving exact solutions of the things for general case and for special initial conditions. And some of that has been made rigorous by myself. And this has been pushed to other models in the context of inverting particles. All right, so on the last slide, here's a quick summary of the status quo about this integrable PD approach. Alexander Kornberg and Pierre, they have derived solution recipe and solution formula. This solution formula depends on knowing the reflection coefficients. The analysis is detailed. They cover the Brownian initial condition that demonstrates symmetry breaking. Okay, and myself have made part of that rigorous. So the general recipe is there. In order to solve for special initial conditions, you need to figure out the reflection coefficients. And there's some non-uniqueness, some very annoying non-physical non-uniqueness. The physical, the reflection coefficient should be just one pair. But if you write down the equation, actually, if you make solutions, and I can now rule them out. So right now it's under that assumption. And there's just some quick open problems. One is removing that uniqueness assumption with this particular initial condition. Another one that I found interesting is this solution formula gives you a solution of PQ of the entire height function. So are you able to do the same limit as I did with Yier to the limit to the most probable shape? That will of course not produce a new result, but I think it's still interesting because that would give us a better understanding of the inverse scattering transform, which probably can be approached by nonlinear statistics design, and also extension to other initial conditions and monitoring conditions. Right, so I'll stop here. Thank you for your attention.
Thanks, Yu-Cheng. Questions? So is this non-uniqueness? Are there any deterministic initial conditions that have the non-uniqueness?
I believe so.
Yeah. And does your math rigorous result include random?
No, it's only deterministic, but includes the one I believe exhibits symmetry breaking.
Okay.
Other questions?
I'm just curious, do you maybe the ones like that, the one that just read? I would guess. Okay, I think I got all the rest.
If there's questions in the chat, feel free to unmute yourself. I had chat. Yeah. No questions. I had a question about fluctuations. So you do the limit shape, but once you do this conditioning, can you control the fluctuations
Not
around it?
No, we do that.
do the physicists have predictions for the fluctuations?
I mean, generally when you do this kind of conditioning, it's believed that fluctuation is Gaussian. But not in this particular context, it's just a general belief.
Okay.
I have one question. So could you go to the slides where you use a Feynman-Kac formula to relate your weight function?
I think I should do it now.
Right, that's one. So actually you are running a random motion backwards to the original, right?
Yeah.
So, and also you didn't like require the direction of the running case. Actually, unground is a planar running motion, right? So I think like, is there any way for us to interpret this kind of expectation of exponentials as some partition function of a planar polymer models here? Right.
Yeah, so that interpretation has some, well, yeah, so that's well, you can definitely interpret this as a partition function, and that's another way to understand stochastic equation. Right, physicists would call that, the partition function of a random the direct polymer internet.
But so I think that because there is another recent work by Iraq, and they also use similar idea, but it's not about the KPZ. I think it was exactly about the KPZ equation, and they use different type of stochastic integral to illustrate or understand the Feynman-Kac representation of that KPZ equation.
Is it two plus one dimension?
Right, it's in 2+1. But
Okay,
yeah, it's in two, and they reduce to the case for the planar undirected case for the random polymer. And I think that is another kind of interesting connection with this project.
Thank you.
Question. So back to that NLS equation we were talking about using the inverse scattering transform is I'm really more I'm more familiar with that. Is there a good way to kind of just from the inverse scattering transform point of view understand what the problem?
Yeah, so it is quite bizarre. So in the typical case where you have I, you would impose an initial condition for both P and Q. And under certain assumption, the mapping from initial condition to the scattering coefficient is bidirectional. Here, both from the PD perspective or from the large deviation perspective, you don't pose just initial condition. You pose initial condition for Q, but you pose a terminal condition for P. That's from both the equation perspective or from the large deviation. From large deviation perspective, the terminal condition corresponds to condition map. And from PD perspective, it's because you see this negative sign here. This thing has to be solved backward. And that fact alone sort of drags the uniqueness completely. The mapping from initial terminal condition to the coefficient is not unique. It changes the whole. The entire game is changed.
Nice.
And I just don't know how to proceed. I just do as I just solve it, and then there's a bunch of non-physical solutions, some of which I know how to rule out, some of them I don't know how to rule out. Yeah, so that's
Very good.
All right. If there's not any more questions, let's thank Chen. And let me make a few announcements. First, let me just stop recording.